So today what we're going to do is we're going to do for torsion what we do for axial loading. So today we're going to cover axial loading. We're going to cover torsion the way we did axial loading when we started looking at all the differential relationships and the general case for axial loading. So today we're going to do the general case for torsion. Now, the last class, we did a very special case for torsion to start introducing our characters for the story. And so we only looked at thin-walled shafts in which everything was constant. So the radius, the thickness of the shaft. Thin-walled means that the thickness is smaller than the radius by a lot, much smaller than the radius. And so we looked at the case in which we had constant torque, constant IP. IP is the polar moment of inertia of the section. So we did this last time briefly, but IP is the polar moment of inertia for the section A. So it's defined as the area integral of r squared dA. So it's something that measures how much area you have, how far from the axis. Okay? So as you see, the units for this one are going to be in meter to the fourth. So the case that we discussed on Thursday was the special case of a thin wall shaft with thickness T. So essentially by defining the radius of the thin wall shaft, I'm telling you the radius for all this area, approximately. So in this case, the polar moment of inertia, the radius is approximately constant. And so when I integrate over the area for a thin wall shaft like that, I get the result that my polar moment of inertia is simply the cross-sectional area of the shaft, which is 2 pi r t, multiplied by the radius. So my radius is big R, and I multiply it by the radius square, and this is my polar moment of inertia for a thin wall shaft. If we do the integral over a shaft which does not have a hole in the middle, something like that, if you do the integral for that, you're going to find that this one is pi r to the fourth over 2, if r is the radius of the shaft. If you just do the integral, you integrate essentially something that looks like that over the thickness of the shaft. And if your shaft is hollow, but is not thin-walled, then you use superposition, and you say the polar moment of this whole thing is the polar moment, say that this one is r out, and this one here is r inner. Then you can obtain the polar moment as pi r out to the fourth over 2 minus pi r inner to the fourth over 2. But what I'm saying is that the polar moment of inertia is the geometric characterization of the cross-section for torsion. You do not care just how much area you have. You care how much area you have and how far from the axis of rotation. So in the special case in which you have a thin wall shaft with a thickness much smaller than the radius, then things get much simpler and everything is constant along the length L of the shaft. Then we obtain this relationship. We introduced shear strain gamma approximately equal to the angle here of that you can construct in the wall of the shaft based on the rotation of the shaft, and it's phi over L R. Remember, this was our twist rate, and of course the angle is dimensionless. We introduce shear stress, and shear stress relates to gamma through a new material property, which is the shear modulus of the material, which is, of course, also in pascals, because this is dimensionless, so the dimensions of G are the same as the dimension of tau, which is a stress, pascals. And we said that if we integrate the effect of the shear stress over the cross-section, this gives me no net force, because every single section here of the circle here is balanced by an equal and opposite effect on the other side, so there is no net force, but there is a net torque. And the net torque, we call it T, axial torque resultant, is defined as positive coming out of the section. And of course, the units are the units for torque, which is Newton times meter. And we obtain that the torque, if I have a shaft of radius r and thickness T, thin-walled, the stress is approximately constant through the thickness of the shaft. And because it is a radius r, I call it tau r. And this is the expression that gives me the resultant from all the stress everywhere. And we can rewrite this one by using the fact that for a thin-walled shaft, this is the moment of inertia, the polar moment of inertia of the cross-section. We can rewrite this as GIP over L times the angle. Oh, there is an angle phi missing here. No, tau r is fine. So the polar moment of inertia times the G over L times the angle of twist. When we put all this together, we get this relationship here, which is similar to the one that we obtained in uniaxial loading, where the axial force was EA over L times delta. So that's the equivalent of that. And because this thing relates the deformation to the resultant, this is called the stiffness of the shaft. So this is the torsional stiffness of the shaft. And you see it as units equal to the units of the axial torque resultant, of course, because the angle of twist is an angle dimensionless. Okay, so this is what we did on Thursday. Now today, what we're going to do is we're going to essentially extend this very simple introduction to the general case in which you may have the cross-section of the shaft that changes along the axis of the shaft. So, and you can have different materials. And you do not necessarily need to have a thin wall. You may have a solid circular shaft to deal with. And your solid circular shaft may be made of more than one material. And the torque can change from point to point. Okay, so today we're going to do the special case of axisymmetric shafts in torsion. Axisymmetric shafts in torsion. So axisymmetric means that the only kind of geometries we're going to deal with are geometries that look like that. Thin wall, thick wall, like this, solid. And you can have solid made more than one material. So the one I drew here is a solid shaft, but I can have cases in which I may have a core. So I may have something that looks like that. I may have a core of one material and a shell around it of a different material. This is okay, I can do that. I can have solid of one material. I can have something with a hole that is thick. But you see, all these geometries, they are symmetric about the axis along which the torque is applied. Okay, so this is a very important limitation of what we're doing in 201. And it will allow us to make a very important assumption about the kinematics of the deformation. Okay, so the first thing we're going to do today is we're going to do the equivalent of what we did in axial loading. So let's go back to axial loading. I'm going to try to make parallel to axial loading as much as possible in this presentation, because I think that it helps to understand where we're going with this stuff. Okay, so in axial loading, what do you think was the single component of what we did that made our life easy? What was the thing that allowed us to deal with things like composite bars, and we knew what to do? What is the important assumption that we made that allowed us to derive relationship between strain and displacement fields and so on? What do you think was the most important thing we did to make our life easy? What do you think? Small displacement helps. That's an important help. And we're going to make the same assumption in torsion. So that's a very good point. We're going to make small displacement. So in this case, we're going to make small gammas, small shear strain. The gamma angle is small. We already used the fact that the gamma is small because we approximate the tangent of the angle by the gamma. The thing that allowed us to go far in axial loading was the kinematic assumption that the cross sections, the whole cross section displaced by u, it stays flat. And it displays rigidly. So if I have a section as section X, what I said is that the whole section moves up by the same amount, right? This is the kinematic assumption that I made in axial loading. The whole section as a whole moves by an amount u. Remember? That is, based on this, we were able to say that the strain was equal to dux dx, and it was only a strain that depends on x. There was no change in strain on the cross-section. This was a huge help for our derivation. The fact that we assume that the section just moves as a whole allows us to say this. Now, we want to do something similar for torsion. So say that I have a shaft attached to a wall like that. And say that I go with a pen, and I drew with a pen a line along the length of the shaft like that. Okay? So this line was sitting here. Okay? Now, something happened. I applied torques. Make another section here just to see how it goes all the way through, right? Now, something happens, and I start twisting the shaft. So as I twist the shaft, it deforms. And this line is going to move down. Okay? So for instance, say that here I move down by this much. So the line now has gone all the way to here. And maybe here I go down even more, maybe here. So the line has gone down like this. And it goes down everywhere along the length of the shaft. You see it? Can you see in your mind that the line that was on top, I turn it, and so the line now looks like that as I twist the shaft, right? Now, the assumption that I make is that as this cross-section moves and it goes from here, now this line has gone here, and here the line has gone all the way down here. See, it was up here, and now it rotates and is here, and here rotates and is here. The assumption that I make is that the cross-sections, as the shaft deforms, every single cross-section stays flat, so the cross-sections they stay flat, and they rotate rigidly by an angle phi. So the whole section, like imagine that there is a disc here at this section, the whole thing rotates by phi. So this angle of rotation here, I call it phi. And the rotation of the section at x, I call it phi of x. Okay? So this is the rotation of every section along the length of the shaft. You see it? So the assumption is that if I paint lines on this section, they remain straight lines because the whole thing rotates. Whatever I drew on this section, if I drew like a little house, the house would rotate rigidly. Whatever I drew on this section stays exactly in the same shape. Okay, the section just rotates. You see? Okay, how much the section rotates depends on when you are along x. So for instance, if I plot phi of x as a function of x, here at the wall, how much rotation will I have? 0. So because this is a wall, at the wall, I'm going to have phi of 0 is equal 0 at the wall. And then I start rotating. I have a little rotation here, more, like I drew it. I'm going to have some phi of x like that. The shape of phi of x will depend on how much loading I put in, what kind of shape of loading I have. And here, where I have phi of L, this is the rotation at the end of the shaft. So phi of x is called the rotation field. The same way as our u of x was called the displacement field. Now here, remember that we used to put a x to remind ourselves this is the x component of displacement, the amount that the cross-section displaces along x. Well, if we have to be precise, this guy should also have an x here, because this is how much I rotate around x. You see? So this one is something that I should put in my rotation, because this is a rotation around x. And indeed, remember that ux is positive with x, right? So ux is positive if it goes along x. Phi x of x is positive if it is a positive rotation with the right-hand rule that rules torsion, positive with x. So if this is your hand, and I have to draw the hand again, this is your hand. Ugly fingers. Okay, so if this is your x-axis, phi of x goes with x. The same way as ux goes with x. It's just that now, because we're dealing with rotation, we cannot just say it points in x. It points in x with the right-hand rule. Okay?
So what does that mean? Like if we made our coordinates so that x is going towards the wall?
Phi of x would be like that. Okay? Phi of x positive would be like this. If I point the x that way, now I point the x this way. So all these phi, see, I'm drawing them positive. If I had made an x that way, this diagram would be underneath the axis, because it would be negative rotations. Okay? So notice that phi knows where x is going. It's not the same as the angle of twist. The angle of twist is the same as the elongation. Elongation doesn't care which way x is going. Elongation positive if I get longer, negative if I get shorter. Angle of twist, positive if I rotate out, negative I'm like the Twizzlers, and I have a negative angle of twist, independent of the rotation, independent of the Cartesian axis. Phi of x is a rotation with x. It depends on the orientation of your axis. Clear? Like ux. Are we good? Wake up. Tough week. You have a lot of exams this week, right? I'm sorry. But you have to stay with me. This is an important class for torsion. OK. All right, so because I'm totally lazy, I'm going to drop this x here. Also because I get tongue twisted if I say phi x of x. So let's call it just phi. But remember that this is the x rotation. OK, so I'm going to drop the x in my notation. But this is phi x. OK, so we have a rotation phi of phi x. And notice that my angle of twist, the big phi, I can obtain it as phi of L minus phi of 0. This is the same thing that I was doing in axial loading when I was saying delta is equal u of L minus u of 0, right? Same thing. The same thing that I was doing in axial loading, getting the elongation from u of x. In torsion, I can get phi of L as phi of L minus phi 0, because if I know, if this is my torsion shaft, if I know how much this thing rotates, say this one rotates this way by phi of L, the deformation is not simply phi of L, because if all of this has the same phi, see, there is no deformation. So what makes it deform is the difference between how much this one rotates and how much this one rotates. If this stays still, this is simply phi of L minus 0. But this one maybe is rotating this way. And then this is negative, and this is positive, and they sum to give you a big angle of twist. Or maybe this one is rotating a little bit this way, and this is rotating more. And so the difference between these two gives you the angle of twist. OK? All right. So now this is the kind of thing we are after. How do we get gamma equal to what in connection to phi x? OK, so this is our next challenge.